given that pk is true, so that completes the inductive proof. So next couple of problems are what are called divisibility problems. So this is kind of the third main type of problem that induction is useful for. So it says that we want to prove by induction that for all n is bigger than or equal to 1, n cubed plus 2n is divisible by 3. So let's write our basis step. So our basis step is, so we're given that n is bigger than or equal to 1, so we're going to say P1. Okay, so P1, I plug in n is 1, and I get 1 cubed plus 2 times 1 gives me 3, and that's definitely divisible by 3. Excellent. Okay, now let's look at our inductive step. All right, so let me pick another color. So same as the other, we want our pk statement. So our pk statement here is that k cubed plus 2k is divisible by 3. Okay, now divisible by 3 you can think of in a couple of ways. You can say that k cubed plus 2k is going to equal to 3 times, let's say, L, where L is an integer. L is an integer. All right, so that's what, if this right here is 3 times any integer, then it's going to be divisible by 3. You could also say that if you have k to the 3 plus 2k divided by 3 equals L equals an integer, that's also divisible by 3. Okay. So my pk plus 1 statement, we're going to replace n by k plus 1. I want to show that k plus 1 cubed plus 2 times k plus 1 is divisible by 3. So this needs to be 3 times m. Okay, you shouldn't use the same integer in both equations, because then you're making a special case instead of the general case. So m is also an integer. All right, so this works well by substitution again. Okay, so again, this is assume that it's true. So this statement here is true. So we want to substitute somehow. Okay, so let's expand this out first. Okay, let's expand this out. We get k cubed and 3k squared and 3k plus 1 and then 2k plus 2. Okay, and I'm not going to write this side right here because that's a question mark there. We don't know that it's equal. We're trying to show that it's equal. All right, let's collect some like terms. So this is k cubed and 3k squared, and then this is 5k. No, let's not do that. Okay, we need to look at our problem a bit closer. I think I can spot what I need to do here. Probably you do too. So I noticed that I have a k cubed. Oh, it's an eraser, that's what happened. I have a k cubed and I have a 2k, right? And I've seen these before, because in the pk statement, k cubed plus 2k equals 3l. So that's where the substitution comes in. So these gets replaced by 3l, 3 times an integer. All right, now let's write what's left over. Okay, so what's left over is the 3k squared and the 3k, and I do the 1 and the 2 is 3. Okay. Again, our goal is to show that this expression is divisible by 3. You can already see that that's turning out to be that way, because everything has a factor of 3. I'm going to factor it out. I get L plus k squared plus k plus 1. All right, so now all we have left to do is to convince ourselves that is this an integer. Okay, so for this to be divisible by 3, we need it to equal 3 times an integer m. Okay, so L is an integer, K is an integer, so K squared is going to be an integer, right? And 1 is an integer. So if I add a bunch of integers together, the result is an integer. So this is indeed 3 times an integer, and this pk plus 1 expression is divisible by 3. So that ends that proof. All right. Okay, so here's another divisibility problem. I'm going to try it out first and then see my steps. Let's look at the basis step. So this is my Pn statement. 7 to the n plus 2 and 8 to the 2n plus 1 is divisible by 57. So again, you can start with, since it's now mentioned, it's up to you. You can start with 0, you can start with 1. If you start with 0, it means that you are proving that this statement is true for non-negative integers. Okay, so let's do that. Let's start with 0. So that says 7 to the 2 and 8 to the 1 is 49 plus 8, which is 57. And 57 is definitely divisible by 57. Okay? Again, when we're proving this, we are proving it for non-negative integers. Okay? Now the inductive step. So the inductive step, we're going to write pk. So pk is 7 to the k plus 2 and 8 to the 2k plus 1 is divisible by 57. So it's going to be 57 times L, where L is an integer. All right. And then we're going to write our pk plus 1 statement, which is 7 k plus 1 plus 2, which is k plus 3. 8 to the 2k plus 1 plus 1. This is going to turn into 2k plus 3. And we need to show that is that divisible by 57. Okay, let me just fix something. That should have been a k there. I'm mixing my n's and my k's. All right, so this is going to be like a little bit of substitution. So pk is true, which means that I'm assuming this equal holds. So I'm going to solve for 7 to the k plus 2. Right, so I'm going to say 7 to the k plus 2 is 57L minus 8 to the 2k plus 1. All right, and this will get plugged into here. Right? So let me rewrite this. So this is 7 times 7 to the k plus 2 plus 8 to k plus 3. This gets replaced by this. So we have 7 times 57L minus 8 to the 2k plus 1 plus 8 to the 2k plus 3. I'm going to distribute the 7. So 7 times 57L. Notice I'm not multiplying these numbers because remember I'm trying to show that the resulting expression is divisible by 57. So if you just leave it like this, you can clearly see that this is divisible by 57. I have minus 7 times 8 to the 2k plus 1 plus 8 2k plus 3. All right. Okay, and we're going to look at this. notice that they both have 8 to exponents. I'm going to factor something. So 7 times 57L minus 8 to the, take the lower power out, 2k plus 1. Actually, I'm going to factor the positive. And then I get negative 7 left over from here, and 8 to the 2 left there, right? Because 8 to the 2 and 8 to the 2k plus 1 adds up to 2k plus 3. We're going to do this. So we get 7 and 57L, and then 8 to the 2k plus 1 times, and this is 64 minus 7, which is 57. Excellent, good. You see there's 57 in both. I'm going to factor it out. And I get 7L plus 8 to the 2k plus 1. Oops. All right, so now we have to kind of say, is this enough? Okay, I was trying to show that this expression right here is divisible by 57. And I found out that I can write it as 57 times this mess. All we need to know about this mess is that it's an integer. Okay, so we can convince ourselves. So L started as an integer, so 7L is going to be an integer. And 8 to any power, 8 to an integer power, let me put it that way, is also an integer. So this is definitely an integer. So M is an integer. Okay, so this is equal to 57 times an integer, therefore is divisible by 57. So that ends the proof. Okay. Now let's look at another kind of induction problem. So we've done 3 so far, like the formulas for the sums, the inequalities, and the divisibility. Okay. You can use induction to prove theorems about sets. Okay, so this says use mathematical induction to prove the generalized De Morgan's law. So remember what De Morgan's law is. So De Morgan, one version of it, has to do with negation, right? So if I have the negation of P and Q, then distribute the negation, but the N turns into a OR. Okay, so that's one with 2 propositions. So the generalized De Morgan's law has to do with more propositions. So what if I have proposition 1 and proposition 2 and proposition N, and I negate it, then this by intuition says it's going to be not P1 or not P2 or not Pn. Right? So we got to prove this. Okay, so I'm guessing that this is the case, but I'm not convinced until I prove it. So we can do that with induction too. Okay, so let's look at the basis step. Okay, so the basis step is basically the regular De Morgan's law. Okay, so if I have 2 propositions, then it works. I know that this is true, right? And I know this is true because it's a law on my list. Now the induction step. Inductive step. All right, so the inductive step, let's write our PK statement is going to be that the negation of P1 and P2 and all the way to PK is going to equal not P1 or not P2 or not PK. All right, so this is taken as true. And our PK plus 1 statement that we're trying to show is that the negation of P1 and P2 and PK with the addition of another statement, PK plus 1, this is going to be not P1 or not P2 or not PK or not PK plus 1. Okay? All right. Again, this is assumed to be true, and we're going to show that this is questionable until we show that it's correct. Okay. All right, so substitution again. So basically, we're going to, let's see, treat this as one proposition. Okay, so it's a combined proposition, but I can say that this is proposition R. Okay, so I'm going to say that not R and pk plus 1 by my basis step, so the De Morgan's law with two propositions, I know that that's true, so that's going to be not R or not pk plus 1. All right, but I know that R means P1 and P2 all the way to pk. And because of my pk statement is true, I know that this part right here is equal to this part right here, so it gets replaced. So this is not P1 or not P2 or not pk with this additional or not pk plus 1. All right, so that completes the truth because I showed that this side is indeed equal to that one. This was an example where you can see that induction works with proving laws of logic, or we'll see later on set theory stuff. All right, okay. Let's see, we have one more thing to do in the section.